I think it's time to start. I'm very happy to introduce the today's speaker, Alexey Garber from the States. So he's going to speak about tilings and in particular about Voronoi conjecture, famous Voronoi conjecture, and probably about its proof for in five-dimensional space, Euclidean space. Okay. Alexey, Losha, please.
Yeah, thank you. And thank you, Andrei and Sasha, for an opportunity to talk. So yes, what I'm going to talk about is the Voronoi conjecture for five-dimensional parallelohedra. And what is about? It's about tilings of Euclidean space with copies of one convex polytope. And particularly the question that I'm going to talk for most of the time is tilings with translated copies of one polytope. So that's basically the main object that we are working about. And yes, I forgot to tell that. So that's based on a joint work with Alexander Magazinov. So, okay. So what is parallelohedron? It's a convex polytope that tiles d-dimensional space with translations only. One particular thing is that usually, and that's basically classical situation, that we consider only face-to-face tilings, which means that that intersection of two copies of the polytope is a face of each of those. So that's not always the case. So for example, for hexagons here, right, so intersection of any two is a face, so it's either a vertex, well, vertex actually is impossible, so it's either an edge or an empty intersection, which is also a face. And here for parallelograms, and actually these are two types of two-dimensional parallelohedra, so or parallelogons, so those are translations that tile the space. So here the intersection is either a vertex or an edge or again an empty set. But for parallelograms, we can also generate the well-known brick wall, right? And there the intersection of some of these rectangles is not a face of both, right? So for example, if I'm going to take this rectangle and this rectangle, then their intersection is 1/2 of an edge, so not an edge. However, if we kind of consider them as degenerate hexagons, everything will be fine, but that's not what we are going to do. So everything will be non-degenerate for now. So what I'm going to talk about, I'm going to talk about these polytopes, their properties, and particularly their connection to lattices and many different applications of lattices. Okay. However, mostly I'm going to talk about combinatorics of such tilings and combinatorics of such polytopes. So these are two-dimensional parallelohedra. For 3 dimensions, there are a bit more than 2. So they were found, all were classified in the end of 19th century by Fedorov. So he listed all types of 3-dimensional parallelohedra, and there are 5 of them. So 2 can be obtained as direct products of a segment with 2-dimensional parallelohedra. So that's a hexagonal prism or a parallelepiped, right? So we just take direct product or Minkowski sum with a segment in a complementary space. The other 3 are a little bit more complicated to get. So, well, these are the pictures. So they are called rhombic dodecahedron, elongated dodecahedron, and truncated octahedron. So the 2 on the left, they have 12 faces each, so that's why they are dodecahedron. So one has faces that are only rhombi, and the other one, there are 2 elongated rhombi or hexagons. The third one actually is the easiest one to construct, because if we extend, so there are 14 faces, so 8 of them are hexagons, 6 are quadrilaterals. So if we extend edges of hexagons, so actually they are going to intersect here in one point, and if we do that for all edges between pairs of hexagons, then we are going to get an octahedron, or there is a way to get a regular octahedron if we use a proper polytope with 14 faces. So what we basically do, we take a regular octahedron and cut out every vertex at 1/3 at each edge. So that's how we can get this truncated octahedron. So now actually a way to travel between these two polytopes is to go from the rightmost to the leftmost. So if we go from truncated octahedron to elongated dodecahedron, so then what we have to do, we need kind of shrink all these horizontal edges, right? So, and then this hexagon will be shrinked into that parallelogram, and so on, right? So actually this parallelogram on top will be shrinked into an edge, but that's fine. And then in order to go from the elongated dodecahedron to the rhombic dodecahedron, we do the same procedure, but kind of shrinking along the vertical direction, right? So we're kind of eliminating that vertical direction. So that's what is called actually contraction, the operation of contraction, but it's not really important for now. That's a way that we can do something with these three polytopes. Let's think about that in that way. So these are all three-dimensional parallelohedra, and there are no others. So that's what was done by Fedorov. And actually, it was done not in a way to find all those polytopes, but more as a study of crystallographic groups, the way how crystals can form in material sciences or in crystallography. So, okay, so these are 5 polytopes. In general, there will be much more, and I'm going to give you a few numbers a little bit later. So here's, for example, a tiling of three-dimensional space with elongated dodecahedra, and it's a little bit different dodecahedron than I had there. So basically, it is the polytope forms layers. So here are 3 layers, and these layers are compatible. So that's really possible. And one thing that is known about parallelohedra is actually that combinatorics of these polytopes is generally enough to say whether they are going to tile the space or not. So these conditions, so these are usually called MINKOWSKI-VENKOV conditions. So there are 3 conditions that are necessary and sufficient for a convex polytope to be a d-dimensional parallelohedron. So particularly the properties, 2 properties, they correspond to central symmetry. So the polytope P itself must be centrally symmetric. Then every facet, so every face of codimension 1 of this polytope should be centrally symmetric as well. And these 2 properties were established by Minkowski. So in the end of 19th century, Minkowski proved that if we have a parallelohedron, then it satisfies these 2 properties. So central symmetricity plays some role there. And then in the middle of 20th century, Venkov proved that actually, in addition to these 2 properties, there is a third one, that that every parallelohedron must also satisfy certain property about projections. So that projection of this parallelohedron, and let me draw a picture here. So if we take a parallelohedron and project it along face of codimension 2, right? So then what we are going to get, so here we are going to get 2-dimensional parallelohedron. right? So it's either a parallelogram or a centrally symmetric hexagon. And actually, Venkov not only proved that each parallelohedron satisfies the additional third property, but he also proved that if there is a polytope, a convex polytope that satisfies these three properties, then there is a face-to-face tiling with copies of that, with translations of that polytope as well, right? So these properties are not only necessary, but they are also sufficient. And also this was independently proved some 20 years later by Peter McMullen. So one particular thing from here is that we are, even if we are not requiring that polytope, that our polytope gives a face-to-face tiling, then it must satisfy these three properties, and in that case, it will have some face-to-face tiling as well, right? So, and that's why I took the part of face-to-face in parentheses, so in the definition of parallelohedron. So from now, we will consider only face-to-face tiling, and actually, there is exactly one face-to-face tiling, right? So particularly, so if we start from a parallelohedron, so let's take one copy. Let's take that one. Okay, actually, that I'm going to define a little bit later. So here should be Minkowski conditions. Minkowski-Venkov conditions. Yes, sorry. So that's a typo that left from another order of slides that I had before. So we have a polytope, centrally symmetric convex polytope that satisfies Minkowski-Venkov condition. Then we can try to tile the space using copies of that polytope. So how can we do that? We will just take this polytope and start to attach it along facets, right? So we translate it and we attach it. Then we translate and attach and so on and so on. Then the theorems of Venkov and McMullen say that we will be able to tile the space, right? So if there is a tiling, then there is a face-to-face tiling, and that's exactly what we're doing here. So what will we get in that case? Well, actually, the centers in that case will form a lattice, right? So what is lattice? So that's integer linear combinations, set of integer linear combinations of some bases, right? So why it is like that? Because every time we have a vector that we can translate by, then we can translate by that vector again, right? Because that's will be the next copy and the next one. So we can get all possible integer linear combinations, and they will form a discrete set. So that means that the distance between two points will be bounded from zero, right? So bounded away from zero, so it is bounded from below by some positive number, right? So it's a discrete set, and it's relatively dense because basically we will tile the space, so we will reach all very distant parts of our space. So that's the only possible the only case when this is possible if the set is a lattice, right? So it's not only that it's discrete and relatively dense, but there is this group structure, right? So we can add any vectors, right? So that's basically makes it a free subgroup of RD and discrete free subgroup of RD, which is relatively dense. That's only a lattice.
Lasha, sorry, can I ask you a question?
Yes.
And in general, actually, is it okay to interrupt you during?
Yeah, sure. I'm sorry.
So is it easy to see this, that if you can tile the space with this with translates, then it should be lattice structure?
Yes. So actually, well, how can you do that? So let's start from a polytope, right? So that's one of the copies. So then it has certain facets, right? So let's F1 through Fn. So these are all the facets. Then for every facet, we can get what is called a facet vector, right? So E with index I. So basically, that's the translation that we need to use to attach another polytope to that facet, right? So another copy to that facet. And then what we have the corresponding vectors, E1, E2, etc., En, right? And now what are the copies that we are going to use? Well, we are going to use all possible integer linear combinations of these vectors. So this is not a basis yet, but basically it's similar properties that we kind of expect from a basis, right?
Okay,
so it's yes, and what we need to do, we just need to take, so this will be a subgroup, a free subgroup of Rn, right? And then we just need to take basically a basis in that free subgroup, and it also will be a basis for the corresponding lattice. Right, so it is already a free subgroup, so we can take a generating set for that free subgroup. So that's how it can be done. So
I'm sorry, I didn't quite understand how Minkowski conditions imply that you can only consider face-to-face tilings.
It's actually, they do not imply that immediately, but that's part of the theorem. So if we have a parallelohedron, then even if it tiles in non-face-to-face way, then this polytope will satisfy these three conditions. And on the other hand, if we have a polytope that satisfies these three conditions, then there is a face-to-face tiling.
Okay.
Right. So instead of considering all the tilings, we can consider only face-to-face tiling. So that's okay. And actually, in some cases, like we saw for hexagons here, there are only face-to-face tilings. Actually, similar thing will happen for these three polytopes. There will be only face-to-face tilings as well. Okay, so this construction basically says that we can start from parallelohedra and we can construct associated lattices. We can go other way around. So if we start from a lattice, so let's start from a set of all integer combinations of some basis, then we can do the construction of the Voronoi polytope or the Voronoi region. So basically what we do, we take one point of that lattice and we construct the polytope that consists of all points that are closer to that point O than to any other point of the lattice. So basically what we do, we construct all perpendicular bisectors and take the intersection, and it's not that easy to see that, but actually the points that will be, well, relatively easy to see actually, the points that are far will not contribute at all. And actually, if we consider the parity classes, so the points where we use the same parities as coefficients for linear combinations, then actually at most 2 from each parity class can contribute those perpendicular bisectors. All others will be far apart. So, and this will give us a convex polytope at this point. Now, if we repeat that construction for all other points of the lattice, then we will get a translated copy of that polytope, because every 2 lattice points are connected with a translation by lattice vector, right? So that's how we can construct copies of the same polytope, which is called Dirichlet-Voronoi polytope of the lattice, or just Voronoi polytope. So that's another construction that starts from lattices and gives us parallelohedra back, right? So we can go from lattices to parallelohedra, we can go from parallelohedra to lattices, and actually the Voronoi conjecture that was formulated in the beginning of 20th century states that this is the only way to get parallelohedra. So if we have any parallelohedron, then it is equivalent to the Dirichlet-Voronoi polytope for some lattice. So not just equivalent in combinatorics, but finally equivalent. So we can find an affine transformation that takes it to the Dirichlet-Voronoi polytope of some lattice. So actually, for this picture, the transformation is the following. So the horizontal vector stays the same, and the vector that looks to the left will be transformed into the vector that looks to the right. So that's kind of that skew transformation. So we are just moving this vertical vector to non-vertical one, or the one that looks to the left into the one that looks to the right. And that's, so the one on the left is not a Dirichlet-Voronoi polytope. And we can see that, for example, because the edges of the hexagons are not perpendicular bisectors to the segments between 2 points, but here they are perpendicular bisectors, right? So all three, actually for other three, it will be the same. And so this is the conjecture, and it's still open in general case. I'm going to discuss a few cases when it is known, particularly in small dimensions, and for some restrictions on the combinatorics of the polytope. But again, it's still open in general case. So, however, there is a very simple proof for two-dimensional case, right? So, for example, for parallelograms, if we start from a parallelogram, then we can transform this parallelogram into a rectangle, and rectangles are exactly Voronoi polygons of the corresponding lattices, right? Because all the sides are exactly perpendicular bisectors, or we can go even more, we can transform those into squares, and these are Voronoi polygons for the standard integer lattice Z2. For centrally symmetric hexagons, it's not that easy, but what is better here is that the transformation is essentially unique, right? So what can we do here? So we can start from a centrally symmetric hexagon, and then we can find an ellipse circumscribed about this hexagon and transform this ellipse into a circle. So basically what we are doing, we're transforming a hexagon into a hexagon which is inscribed in a circle. And then this particular hexagon will be a Voronoi polygon. So why it is like that? Actually, we can, so I can go back to that picture. So if I'm going to look on the vertex, which is common to some 3 hexagons, then for Voronoi polygon, so it is equidistant from the center. So these 3 segments will be of equal length. And now if I copy the translated copies of these segments, then I'm going to get all 6 segments that connect to this point here in the middle with 6 vertices of the hexagon. So basically this is the, for two-dimensional case, this is a necessary condition that these 6 points, 6 vertices of a hexagon must be on one circle. So this will not be true in general case for higher dimensions, but for two-dimensional case, this works. And actually, this transformation from ellipse to circle is essentially unique, right? So we just need to shrink or stretch along one direction. And after that, we're going to get a Voronoi polygon. So that's a proof of the Voronoi conjecture in dimension 2. In higher dimension, it's not that easy. So what is known in higher dimensions, so for R2, it's treated as folklore. I don't know where the proof was first found. For R3, the 3-dimensional parallelohedra are known since the end of 19th century. So actually, so actually it is possible to check that they satisfy the Voronoi conjecture. And another way of doing that was done by Voronoi, and that's what I'm going to discuss a little bit later as well. So you can do that kind of other way around. So instead of finding all parallelohedra, so you can find all Voronoi parallelohedra, so all parallelohedra that satisfy the Voronoi conjecture, and we will get the same list essentially. So, and that proves that all these satisfy the Voronoi conjecture. But it's also treated as a folklore because I haven't seen any direct proof stating that for three-dimensional case we can do that. We can use that technique to prove the Voronoi conjecture. For four-dimensional case, the result, the Voronoi conjecture was proved by Delaunay. And first he proved the Voronoi conjecture and then used that to find a classification of four-dimensional parallelohedra. So actually, he found 51 of those parallelohedra, so he missed one. And the last one was noticed by Stogrin when he was studying properties of crystallographic groups, right? So he found the additional one. So in total, there are 52 four-dimensional parallelohedra. And in five-dimensional case, so that's the main theorem that I will try to reach today. So the Voronoi conjecture is true in five-dimensional case, and that's what we proved with Sasha Magazinov about a year ago. So there were attempts, or there were claims that the Voronoi conjecture should be true in five-dimensional case, particularly one done by Peter Engel. But instead of that, instead of proving the theorem, he was attempting to give a classification of all Voronoi parallelohedra, and he said, okay, we're unable to find something that, or classification of parallelohedra, so we're unable to find those that do not satisfy, so the Voronoi conjecture should be true. But that's not actually the rigorous proof for Voronoi conjecture in dimension 5.
Alexey,
So,
can I, at this point, can I ask you something? So you
yes.
mentioned this this affine, so you want affine equivalence. If you relax it to like every parallel hedron is affinely equivalent to the Voronoi cell of the lattice. But what if you ask only combinatorial equivalence? Is it trivial? Is it easy?
It is not known.
It is either not known or also
yes,
not known. Yeah.
It is also not known. Actually, one of the steps that I will discuss uses that kind of combinatorial equivalence. And actually, one thing that is known, and I'm going to discuss that as well, so that there is no known parallelohedron such that its combinatorics is not enough to give the Voronoi conjecture. So for all parallelohedra that we know, combinatorics alone is enough to force the Voronoi conjecture. So it's kind of a geometric conjecture, but apparently combinatorics alone is enough. And moreover, right, and that's something that is also a little bit puzzling, that if we have two parallelohedra with the same combinatorics, then they are, well, these two parallelohedra are not necessarily affinely equivalent, right? So for hexagons, as I said, right, so there is essentially one affine transformation, and for most of parallelohedra, there is essentially one affine transformation. But if we have two combinatorially equivalent parallelohedra, then there are dual tilings, and these dual tilings will be affinely equivalent right away. So combinatorics of parallelohedra somehow fixes the affine class of the dual tiling. Right, so basically it should be that combinatorics is enough, but there is no proof and there is nothing known either. So in general, when we are talking about classification of parallelohedra, it is easy to see that there are only finitely many of them, combinatorially finitely many of them. Because, right, so this, let me go to that picture. So if I consider the parity class of this lattice, right, so that's, no, that's the wrong one. So this is a parity class. Then if I pick one parallelohedron, then this parallelohedron has at most 2 neighbors along facets from this parity class, right? Because actually 3 are too far apart to have something in between, right? So we can have it in the case of parallelogram, but then it's not a facet, so those are just edges. And and that means, so we have in total we have 2 to the d parity classes. So one that this particular parallelohedra is in cannot give any facets. So that's the upper bound on the number of facets of each parallelohedron, and there are finitely many different combinatorics with that number of facets. But that's a huge number, right? And it's impossible to give any reasonable upper bound on the number of parallelohedra and any reasonable classification of all parallelohedra to check for them the Voronoi conjecture. Even I think in dimension, even in dimension 3, it will be tough because the upper bound will be there 14 faces, and that's a lot, right? So there are a lot of polytopes with 14 faces.
Do parallelohedra generate any flat tori or maybe Calabi-Yau surfaces or any flat surfaces in corresponding dimensions?
I don't know. I know nothing about Calabi-Yau surfaces. For flat tori, well, you probably can factorize by the lattice, and you get some kind of tori, but that's you probably will get some kind of you just use that the parallelohedra are fundamental regions for the corresponding groups, and I think geometrically that will not be different from the tori that we obtain from parallelepipeds.
Okay.
But I don't know. From that part, from that topological point of view, I don't have an answer.
Losha, I have a silly question. Am I right that the strategy in general is the following? First, you prove some kind of classification theorem, and then you check the Voronoi conjecture for every representative in this classification theorem one by one. Or there are some kind of general tools, some kind of general criteria to verify the Voronoi conjecture.
There are general tools, and so that's what I'm going to talk about, these general tools here. So that's what is called canonical scaling. The reason why the approach of classification first and then checking doesn't work is that there are just too many of them, and the restrictions are relatively mild, right? So we have those central symmetry, we have upper bound on the number of facets, and that's, well, and we have that projection property, and that's pretty all the restrictions that we have. And just the number of faces, right? So let's, for example, in 4-dimensional case, that will give us 30 facets. I'm not sure how many polytopes with 40 facets there are in 4-dimensional case, but I assume that a lot, right? So, and very much a lot of those are not parallelohedra, so it's complicated to classify. So there is an approach to get some kind of classification, and that's was done by Delano while proving Voronoi conjecture in dimension 4, but it's not classification of parallelohedra, but classification of local structures that can appear there. And that's a little bit different, and that may work. But in general, first, the idea is to prove the Voronoi conjecture, and classification actually appears after. So because for the if the Voronoi conjecture is true, then we can kind of enumerate all possible lattice structures that we have there. So it is known that there are finitely many crystallographic groups. So here it's even a bit simpler because we are not interested in all kinds of rotations, reflections, and so on. So generally, classification is more complicated without assuming the Voronoi conjecture.
Okay.
Okay, so that's the conjecture. That's the theorem that I want to talk about. But before that, so let me talk a little bit about history. So particularly about Hilbert's 18th problem. And what that problem is about, it's about lattices in d-dimensional space and their properties. So particularly, there are three parts. So the first one asks about finiteness of the family of crystallographic groups. So what are crystallographic groups? So those are the groups. So these are discrete discrete groups with compact fundamental domain. And compact here, right? So we kind of consider that fundamental domain up to measure 0, right? So they can intersect by intersecting boundary points. So those are the groups that are used in crystallography and particularly in classification of crystals, though it is not that straightforward, right? So that crystallographers do not use kind of the same types of groups that mathematicians will prefer to use, but there is a translation from crystallographic language to mathematical language and the other way around. So the second part is about existence of a polytope that tiles d-dimensional space, but is not a fundamental region of a crystallographic group. So basically, how can we find polytopes, or how can we construct polytopes that tile space? So we can take a crystallographic group, right? So, and then we can take an orbit of one point under that crystallographic group and take the Voronoi region. So actually, that's what is called Dirichlet polytope for, or Dirichlet stereohedron, right? So then that construction is due to Dirichlet. So then after that, since it is fundamental, so since this is since this will be fundamental region, then this polytope will tile the space, right? So because if we copy that, so if we take the orbit of that fundamental region, then it will give us a tiling of the space. But the question is whether there is a polytope that cannot be obtained in that way. So it still tiles the space, but not a fundamental region. And the third question is about densest sphere packings. Actually, it's not sphere packings, but any object. So densest packing with any object in R3, which is more known as Kepler conjecture in the case of spheres. So, and the best known packing, and actually the problem is solved, right? So the best known, the densest packing is related to lattices. Unfortunately, this is not the case for some higher dimensions. So there, the densest sphere packings is not always the densest known sphere packing is not always a lattice one. But for Hilbert's problem, all these were solved. So the first one was solved by Bieberbach, who proved that this finiteness property, and basically Bieberbach proved that in every crystallographic group there is a subgroup of finite index that is given by a lattice, right? So the dimensional free subgroup. For the existence of a polytope, the examples were constructed by Reinhardt in three-dimensional case and by Hayes in two-dimensional case. And those are, so for Hayes, it's a non-convex polygon, and the same with Reinhardt, as far as I remember. And for dense sphere packing, this problem was solved by Hales with many co-authors. So actually, first he proved it using some computational tools in 2005, and in 2017, that computational proof was formally verified by another software for verification of proofs. Right, and that's where he has many co-authors. So all these are solved, and all these problems involve tilings with one polytope, not always convex, not always lattice one, but some tilings. Another question which is also related to this problem is, well, which convex polytopes may tile the space? For non-convex, it's not really that interesting, because we can start from a tiling with a square and then make something artificial. Yes, for hash, it was in R2. Was it? Yeah, so hash in R2. So and here for squares, we can make some crazy decoration here, and we can make it on every horizontal side, and that will make it non-convex polygon with basically any number of sides, right? So if we take this union. But for convex polygons, it's easy to see that 7 gon cannot tile the plane, and it was relatively easy to get a classification of all hexagons. For triangles and quadrilaterals, all of them can tile the plane, but for pentagons, that's where the problem was open for a long time. And actually, during the last 50 years, I think there were additional types of pentagons that were found and that are that can be used to tile the plane, and including some amateur mathematicians who are really not mathematicians as their main job, but they're doing kind of recreational mathematics, and they were drawing pentagons, and they were able to find new types. So finally, some 3 years ago, Mihail Rao announced computer verification that all the types that are known so far.
Translations of pentagons, so just as for hexagons.
Excuse me?
You have pentagon and all, and some translations. It's translations, yes?
No. So now we are not about translation. So that's the question is for if the only translations are allowed, then it's only parallelogram or centrally symmetric hexagon. Here, in general, right? So here, so not translations only, right? So that's, so thank you. So it's not translations only. So for example, for the simplest one, for pentagon, we can start from something like that, then attach another copy here, and then just copy that rectangle to tile the plane, right? So, and actually, it's not even edge to edge. So all the types are considered. So for pentagons, the final result was announced by Rao, but as far as I know, it's still not published yet. So maybe it's still under the paper is still under review. And there is
actually I have a tiny comment about Rao. So I happen to know him, and apparently he was contacted by some French designers after this happened. So it was somehow a big news and got to the media, and some French clothes designers were contacting him to design some things.
Yeah.
So that was quite interesting. Even though he didn't find a new one, he was sad about it. Actually, he wanted to find another one.
Yes. So he verified that there are no others. So and in three-dimensional case, the question is much more complicated, and even the maximal number of facets that a polytope can have in order to tile the space without using translations only, with all possible rotations, reflections, and so on. So that one is not known. So there is an example by Peter Engel with 38 facets, and actually the way it is constructed, so there is what he did, he took a crystallographic group and an orbit of 1 point under that crystallographic group, and then took Voronoi tiling. So Voronoi tiling of an orbit of that crystallographic group. And that's how, so that's why what you can get is called a Dirichlet stereohedron. So he got a Dirichlet stereohedron with 38 facets. And the upper bound for the number of facets, so the best known upper bound is due to Paco Santos with co-authors, and it's 92 facets. So there is a series of 4 papers related to different types of crystallographic groups. So the one that they got is 92 facets, so that's an upper bound. But what is in between, it's unknown. Actually, the first bound was found by Delaunay in 60s, I think, and that was about 340s for the number of facets. So that's from 340 to 92 is a good improvement, but still there is a gap between 38 and 92. All right, so even for that case, it is unknown whether we can find any polytope with more than 38 facets that can tile three-dimensional space. Convex polytope, yes.
Stereohedron means literally that a convex polytope that tiles the
space. Convex polytope that tiles the space. So actually, stereohedron, so the word parallelohedron is not because it tiles the space with parallel translations, but because the opposite faces are parallel. So that's basically was the meaning to introduce the word parallelohedron, because there are parallel facets, not because we use parallel translations only. Okay.
340, what is this estimate? Estimate of what?
So that's the same. So that's the original bounds that Delaunay had for the number of facets for Dirichlet stereohedron, and that was improved by Santos. Another application where parallelohedra are used, though they are used kind of implicitly, so that's the problem of lattice covering. So that's kind of, well, not really dual to the problem of sphere packings, but similar to that. So what we are doing, so for given dimension D, we're trying to find a lattice that gives optimal covering of d-dimensional space with balls of equal radius. And it's not that straightforward to define optimal as with packing problem, because for packing problem, so we just have spheres or balls that do not intersect, and we just calculate the density of the space which is covered, and that's the optimality. We want to make this density as large as possible. For covering, it's not that straightforward, because here our spheres will intersect, right? So it's unclear how do we count that doubly covered region, or there will be triply covered region, so whether we give any weights or not. So actually the classical approach is that we consider the lattices or the point sets with given density, and we try to minimize the radius of the covering. So basically it's minimize radius, so minimize radius for given density. And this problem is solved in small dimensions, right? So it is solved completely in dimensions from 2 to 5. And in all these cases, the lattices are dual to lattice AD. In dimensions 6, 7, and 8, there are examples only of best known covering. So these are not complete proofs, right? So and those are those are lattices that are different. So actually, those lattices give better covering than the lattice dual to AD. And that's so these results are obtained by Schurman and Valentin. So in 5-dimensional case by Ryzhkov and Baranovsky, in 4-dimensional case by Delaunay and Ryzhkov, in 3-dimensional case by Bamba, and in 2-dimensional case by Kirchner.
What is AD? What is AD?
So AD is one of the root lattices. So as far as I remember, so this is the lattice in D+1 dimensional space where sum of coordinates is 0, right? So and those are integers. Right, so this is a d-dimensional lattice, but I may be wrong. I may be mixing it up with D with D. D, probably no, right? So because I think DD is the lattice where the sum is even, right? So okay, that's as far as I remember from the top of my head. So, and these results, the results in dimension from 4 to 8. They actually use reduction theory, and that's what I'm going to talk shortly. So they use reduction theory for lattices, and which is equivalent to a partial classification of Voronoi parallelohedra. So that's what is where parallelohedra are used. So basically, classification of parallelohedra can be used there. So and additional situation where parallelohedra are used in many situations. So that's lattice algorithms. So particularly there are 2 NP-hard problems related to lattices. So these are NP-hard. And one is the shortest vector problem. So, and that's the problem where we need to find the shortest non-zero vector of a given lattice. And that's related basically to the lattice packing problem, sphere packings using lattices, because if we have 2 spheres, then what does mean that we cannot increase the radius of that sphere. So that's that means that we have this vector as the shortest one in the lattice, right? The other question is the closest vector problem, and that's where we want to find a vector closest to the target vector. So vector of the lattice closest to the target one, and that's actually relevant to the sphere covering problem, because if we have vectors of our lattice, so x1, x2, x3, and so on, and this is our vector t, so then we want to find the one, so the sphere that will cover this vector t, and that's pretty much the same as finding the closest vector. So that's basically we want to maximize that minimum among all these vectors t, and that will give us the covering radius. And these, so as I said, these questions are NP hard. So solving any of those in polynomial time will basically give some insight in P equals NP, right? However, those that are known, there are only exponential algorithms to solve these problems. But these problems are used in a variety of applications. So in Lenstra-Lova's algorithm for lattice reduction, or for polynomial factorization over Q, for solvability, for integer optimization, for cryptography, basically for many major lattice problems. So one of these is used, and actually they are kind of interchangeable. So there is a way to transform from one to the other in exponential time as well, right? So each one is exponential, so moving between in exponential time is not that bad. So that's basically algorithmical point of view. And one additional application that we found pretty recently, actually, parallelohedra are used in functional analysis as well. So, and particularly in the theory of spectral sets. So a set is called spectral if it is bounded, measurable with positive measure, and there is an orthogonal basis of exponential function in the L2 space. So exponential functions here are the functions of the form, so exponent of I times inner product of lambda and x, right? So x in here is in RD and lambda are in our set, right? So in that case, so this set lambda is called the spectrum of our spectral set, right? And there was a conjecture by Faglid from 70s that a set is spectral if and only if it tiles d-dimensional space with translations. So one particular thing here is that we do not require that this set to be convex, and it's not required even to be connected, right? So it's any measurable set. And actually, that's the reason why there were counterexamples found in 5-dimensional case by Tao, in 4- and 3-dimensional case by Matolchi and Kalantzakis. But for convex sets, the Faglid conjecture was proved by Lev and Matolchi also a year ago. So basically, they showed that every convex spectral set is a parallelohedron and every parallelohedron is a spectral set. However, this part was shown by Faglid, and actually in this case it's relatively easy to find the spectrum. So the spectrum will be the dual lattice, right? So if we have a tiling using the using lattice translations, then the spectrum will be given by the dual lattice. Okay, so this was basically the history of where parallelohedra appear. So one particular case why parallelohedra appeared in the work of Voronoi, and that's basically the approach to find all parallelohedra, or more specifically all Voronoi parallelohedra. So that's what is called reduction theory, right? And in general, reduction theory is a theory of finding optimal basis for a lattice, right? So for example, if we have a 2-dimensional lattice, then of course there are many ways to find a basis. So one is the standard one, so 1, 0, and 0, 1, and that's a very nice basis. However, we can find something very bad, right? So for example, a basis that consists of vectors 10, 11, and 9, 10. So this is also a basis, but much worse, because the vectors are pretty long, right? So the vectors are like that, and there is a very tiny angle between these two vectors. And now if you want to write any vector of this lattice as a linear combination of vectors here, then we can do that, but the coefficients will be ugly, and the computational part of finding that may take much more time than doing that with these simple vectors, and the error will be worse, right? So, and that's what is reduction theory is about. So choosing an optimal basis, and actually optimal here can have different meanings. So one example, as I have it here, is choosing the shortest possible vectors at every step. Another way is to, and that's what is was basically done by Voronoi in his reduction theory, is find an optimal basis such that the dual tiling, if it exists, actually it will exist, will have some nice representation, right? And the dual view here is that if we have a lattice, then from this lattice lambda, then we can choose a basis and find the Gram matrix. And then what we want to do, we can find, so we want to find a matrix in the group of integer invertible matrices of size D, such that the corresponding matrix, right? So the corresponding matrix A transpose GA will have an optimal representation, right? So, or instead of Gram matrix, we can use the positive definite quadratic form defined by that matrix, right? So because the Gram matrix is positive definite. So what are the dual tilings? And actually the dual tilings are, for Voronoi tilings, the dual tilings are well known. So those are what is called Delaunay tiling. And the classical approach, and actually it was introduced to some extent by Voronoi, and then later Delaunay formalized it for arbitrary sets and in arbitrary dimensions. So basically Delaunay tiling is the tiling using empty spheres. So if we have a point set, well, for me this point set will generally be a lattice, then we're going to say that a full dimensional polytope is in the Delaunay tiling if and only if it is inscribed in some empty sphere. So how can we get it? So we can just pick a point and then start to inflate that sphere. So as soon as we get a full dimensional set on the sphere, we stop and we say, okay, this is going to be our polytope of the Delaunay tiling. And in general, the polytopes of the Delaunay tiling, they form a tiling which is metrically dual to the Voronoi tiling, right? So metrically dual means that their faces of complementary dimension are orthogonal, right? So particularly here, so the blue tiling is a Delaunay tiling, the black tiling is the Voronoi tiling, and the edges are perpendicular. So what is the reason for that? Because actually, if we are going to take a vertex of the Voronoi tiling, then the corresponding centers of the polytopes will be equidistant. So that means that we found an empty sphere, right? So it's the closest point, so we found an empty sphere. And actually, we can go other way around. We can go, we can do that for the faces of smaller dimensions as well. So what is a way to construct all the tilings? And that's once again shows that they are dual. So that's what is called the lifting construction, and it works not only for lattices but for arbitrary point sets which are finite or infinite. So we lift all the points of this point set onto the paraboloid, the standard paraboloid x transposed x in D+1 dimensional space, and then we do two different constructions for this point set. So for the Voronoi tiling, so let me draw this paraboloid. So for the Voronoi tiling, we construct the tangent hyperplanes and take the upper half space for each hyperplane, and then project this infinite polyhedron back to the D-dimensional space. And the projection of the faces, so actually we need to project D faces, right? So the projection will give the Voronoi tiling. Now, if instead of taking the tangent planes, we're just going to take the convex hull and project it, right? So again, then we're going to get the Delaunay tiling. So while the problem is with finite sets, then we're going to have kind of two layers, the upper part and the lower part. So we need to project the lower part only. And this is actually based on a simple construction using parabolas. So one simple construction is the following. So if we take a parabola in two-dimensional plane and take two tangent lines, then the lines parallel to the axis of this parabola through 2 points on the parabola and through the point intersection. So this one through the point of intersection will be exactly in between the first two. And that's for the Voronoi tiling. For the Delaunay tiling, actually, we need to take a paraboloid and intersect it with a plane. Then the intersection projected on the plane will give us a circle. So that's another geometric property which is also relatively simple. So
what is half
basically,
spaces? Upper half spaces. In what sense upper half?
well, if we have this paraboloid y equals x transpose x, so then basically its axis looks upward, so that's the y-axis, and we take that part that so we take the part that deals with let's call it positive infinity for every with y, right? So basically it's the part let's okay, let me try to write it down. So okay, so if we have y, which is x1 squared plus x2 squared plus and so on,
and the part that has no this has vector that has positive scalar product with y.
Yes, the positive scalar product with y, but actually
not arbitrarily large. Yeah,
actually you can write it explicitly. Now if we take a point on the paraboloid, so the point a1 through AD. So if this point is on the paraboloid, so let me do that here. So so if we have this paraboloid x1 squared plus etc. plus xd squared, and we have a point on that paraboloid, then the tangent plane will be a1 x1 plus and so on plus ad xd, right? So if our point is a1 through ad, so then this equation will give us the equation for the tangent plane. And now I just take the inequality, so y is equal to is greater than or equal to a1 x1 plus and so on plus ad xd. So this is upper half space. So basically, y can be as large as possible, as large as well, we take the part that has positive values for not positive, so positive infinity for y as limit point. Let's call it like that. Okay, did I answer the question?
Yes, thank you.
Mm-hmm. So and basically the approach of the Voronoi reduction is to use instead of finding all parallelohedra, is to use different metrics when studying the same lattice. So basically, we take an affine transformation for parallelohedra or for dual tiling if it exists, right? So so we take an affine transformation that takes the lattice into the standard integer lattice. Then, in that case, Delaunay tilings will transform in something else, into non-Delaunay tilings, but those will be Delaunay tilings defined with respect to different quadratic forms, right? And the task now, and basically that's was the problem of the Voronoi's reduction theory, right? So he was studying the reduction of quadratic forms and how we can solve. So how can we find minimums of quadratic forms, right? So basically, initially it was a work on number theory rather than on geometry. So it works. So find the minimums of quadratic forms at integer points, right? So and the task was to find all combinatorially different Delaunay tilings of d-dimensional lattice. Now, we define Delaunay tilings only for one particular case as empty spheres, and that's not that there is not much difference for integer lattice. We have just one, but now we define the Delaunay tiling with respect to arbitrary quadratic form, and the only difference is that now instead of using empty spheres, we are using empty ellipsoids. And this approach is kind of a little bit better than trying to study parallelohedra. And the reason for that is that, or even Voronoi parallelohedra, because if we change the lattice a little bit, then parallelohedron will change, right? So the perpendicular bisectors will move a little bit, and that means that the parallelohedron will change, right? So combinatorially, it's not always going to change, but geometrically, it will change. But for diagonal tilings, now we have a fixed set of vertices, the integer lattice, and now if we try to change the quadratic form, well, then the set of vertices will stay the same because it is fixed. And the only change that may happen is that there will be some change in polytopes. And actually, this change will be either subdivision of large polytopes into smaller polytopes on the opposite one. So we can take a few smaller polytopes and take the reunion. And in general, the Voronoi's approach was to define the set of quadratic forms that give the same diagonal tiling. And one thing that he did, he proved that this, what is called the secondary cone, is a convex polyhedron in the set of all positive definite quadratic forms. And actually, there are only finitely many essentially different such convex polyhedra. So there are only finitely many classes under the action of, so basically under the change of basis in the integer lattice. So that's the theorem here. So actually, there are two types of classes. There are notable, well, there are more that are notable, but two that are kind of on the different parts of the number for the number of degrees of freedom. So in that case, if we have the secondary cones, which is full dimensional, so secondary cone which is full dimensional, that means that small change in the quadratic form doesn't change the Delaunay tiling, and these correspond to Delaunay triangulation, so where we have only simplices in our Delaunay tiling. So in that case, if we have a Delaunay triangulation, then we also cannot change it by minor change of the quadratic form, right? So that's also easy to see because it means that these spheres or the ellipsoids are empty, and if we change the quadratic form, then the ellipsoids change a little bit, so no additional point will appear on this ellipsoid. The other part is one-dimensional secondary cones, and those are what is called extreme rays, and those are that basically will change always, except if we multiply the corresponding quadratic form by some positive number. And how can we find the classification? Actually, the classification of the corresponding secondary cones is used under the action of this group of invertible integer matrices, and we can show that two Delaunay tilings are finally equivalent if and only if the corresponding cones are equivalent under the action of this group, right? So there is a matrix that transforms one cone into the other. Okay, so let me show you.
Alexey, can I quickly ask you the?
Yes.
So can you again look at this definition of, or maybe you say a couple more words about secondary cones?
Yes.
To get some intuition.
Actually, I'm going to.
And also another thing, just so that you know, is that you say like 20 more minutes or something like that.
Okay. Yes.
Or maybe 25.
Okay.
If we want to stretch it a bit.
Yes, I'm actually the next part will be a little bit more pictures, and then I'll start to prove something finally.
Yeah.
Yeah. So secondary cone is basically, so we fix a lattice, which is the integer lattice, and now we take all quadratic forms that define the same Delaunay tiling, right? So the Delaunay tilings could be different, but if we take one Delaunay tiling, then we can choose all quadratic forms with this particular Delaunay tiling. So basically, it's some kind of dual approach. So instead of changing a lattice, I'm changing the way I measure distance. And it's kind of the same because if I'm changing the way I measure distance, I can make an affine transformation where this new distance is the standard Euclidean distance, and it will give me a new lattice. But here, as I said, the integer points are fixed, so we are kind of working with only discrete changes rather than continuous changes. So in general, yes, so that's the definition. So we start from some Delaunay triangulation, and we try to find all quadratic forms that give that Delaunay triangulation. And actually, it's possible to do. So let me go directly to the pictures. So, and I'm going to construct all secondary cones in two-dimensional case. So there, every positive definite quadratic form is defined by three parameters, A, B, and C. And well, actually, there are inequalities, so that A and C are positive, and that determinant is positive as well. So that's enough. So the set of those cones, quadratic forms, can be represented as a cone over, right? And so we'll try to construct the secondary cone of one triangulation first. So this is a Delaunay triangulation, and actually, if we consider dual, then it's going to be so there is going to be a tiling with these hexagons, right? So it's a Voronoi polygon. So it's a Delaunay triangulation here. So now let's try to find the secondary cone of that triangulation. And actually, similar to construction of the Voronoi parallelohedron using perpendicular bisectors, we can do that using kind of local approach, right? So we can take a pair of adjacent triangles, right? So here this pair, and they share a side. So now what we want to understand what does it mean that these two triangles are exactly like that, so that this side divides this square into these particular two triangles. And actually, this condition corresponds to one linear inequality for the entries A, B, and C. Why it is like that? Because now if we take this local picture and lift it to the paraboloid y equals x transposed qx, right? So then what we want to have that this vertex will be above the plane defined by this triangle, right? Because Delaunay triangulation, we need to take the convex hull and project it back. So this point, so this triangle should be part of the convex hull, so this additional point must be higher. And actually, the symmetric condition that this point is above that triangle. And that's one linear inequality, right? So point above plane, that's a linear inequality. So for this particular case, the inequality will be that B is less than 0. We can repeat it for another pair of triangles, and that's B plus C is greater than 0. And for the third pair of triangle, which is the red pair, then it's A plus B is greater than 0. And that's it. So why it is enough? Because actually every edge of this Delaunay triangulation is a translation of one of these three edges, right? So there will be no additional conditions because all the conditions are listed here, right? So this horizontal edge will give us the same condition as there because Delaunay triangulation is respected by translation. So that's it. We have constructed the secondary cone of that particular Delaunay triangulation. So actually, in general case, it will be much more complicated to do that because for higher dimensions, there will be many facets, and in general, there will be many redundant inequalities. So I think for 5-dimensional case, there are a few thousands inequalities, but the maximum that we have non-redundant is 20. So we need to eliminate all those redundant inequalities, and that's computationally takes some time. So here we have a secondary cone, which is a cone over a triangle. One unusual thing here is that we have 3 vertices of that triangle are represented by non-negative quadratic forms, and that's why they are on the boundary here. But inside we have all the quadratic forms that correspond to these Delaunay triangulation. And actually, we can do that for other Delaunay triangulations here, and those that are neighbor in the cone, they differ by a bistellar flip, right? So you can see how the edges inside squares are flipping from one direction to the other. And those that are not
excuse me, do we have any group action on the set of bistellar flips?
Group action on the set of bistellar flips?
Yeah, so here, when we pass from one, so when we have some, say, triangles or some fundamental domain, there should be some nice group acting on when we reflect or when we do something.
I am not sure, really, because, well, I know that there is a group acting on the tiling on the set of secondary cones, and that group is GLD of Z. But for the set of bistellar flips, there could be one, but I am not sure. Well, in 2-dimensional case, it's easy, right? So it's because the bistellar flips are easy to find there. It's for a 3-dimensional case, it's also will be relatively easy, but for higher dimension, I'm not sure. So
if you give a talk on Monday, I would be happy to discuss it.
Okay, yeah, sure. Yeah, and I saw your question about the example of tau. I don't know. I know nothing about specifics of tau's example and how it corresponds to any arithmetic progressions there. So I just know that it exists, and actually it can be generalized, I think, not only for. So it started not from Euclidean space, but started from I think arithmetic progressions in field of characteristic 5, maybe, but I'm not sure. I don't want to give any incorrect answer right now. Right, so here we have bistellar flips, and those cones that are not the cones of full dimensional, they correspond to Delaunay decompositions, but not Delaunay triangulation. So for example, this one, and if you remember, what are these 2 vertices? So one vertex was 1, 0, 0, 0. This one, 0, 0, 0, 1. So if you add those 2 matrices, then you get the standard Euclidean metric, and that's exactly the Delaunay triangulation for the standard metric. Right, so that's how we can see that as well. And in general, we can use that approach, right? So we can start from one triangulation, then we use all bistellar flips to construct all neighbor Delaunay triangulations, and so on, as long as we are able to check them for equivalence under the set of integer matrices, then we can find all possible Delaunay decompositions. And actually, that's what we did with Mathieu Dutour, Sikirich, Achille Schurman, and Clara Waldman. So we found this scary number of affine types of Delaunay subdivisions, and those are combinatorially different Voronoi parallelohedra. So it's not a classification of all parallelohedra, but also only classification of all Voronoi, but only of Voronoi parallelohedra. Okay, so that's how reduction theory helps in finding all parallelohedra. So now let's, I think I have about 10 minutes. So now let's finally talk about the proof of the Voronoi conjecture. So there are basically many combinatorics involved in the proof. And the first thing that we do, and actually that approach was used by Delaunay for 4-dimensional case, is to find whether the parallelohedron can be extended. And if you remember my description of truncated octahedron and 2 other 3-dimensional polytopes, so that's what is called shrinking or contraction. So the opposite operation is called extension. And in that case, we can show that the extension has combinatorics of one of those polytopes. And actually, another result that can be used here, that in 5-dimensional case, we can use global combinatorics to enforce the Voronoi conjecture. So global combinatorics of a Voronoi parallelohedron actually is enough to enforce the Voronoi conjecture. So particularly if there is a parallelohedron which is combinatorially equivalent to the Voronoi polytope, then it must satisfy the Voronoi conjecture as well. And finally, the last building block is local combinatorics, right? So, and that's what I said on the question that Sasha asked, that classification is impossible, general classification is impossible, but it's possible to find how locally all tilings by parallelohedra could be designed. And actually, this is also goes back to the Delaunay tilings, because if we have a tiling with Voronoi polytopes, then the dual tiling, if it exists, must be a Delaunay tiling, right? And for Delaunay tilings, again, we know how to find all possible Delaunay tilings, at least in small dimensions. Okay, so what is extension about? And I think I'll have time to talk about extension. So one thing is that if we have a parallelohedron, then we can try to extend it. And extension here means that we add a segment as Minkowski sum. So if this segment is in complementary subspace, right? So if we work in higher dimension, then it's just taking direct sum. In general, it's just adding a segment as Minkowski sum, so making it kind of extended. And in that case, this direction or this segment is called the free direction. And we can extend it if we have a parallelohedron that we can extend it, then we can extend it further. So basically, we can make it kind of very long. And this was used by Grishukhin, Vek, and Magazinov to basically prove that the Voronoi conjecture is true for P if and only if it is true for its extension, if there is an extension. And another situation where the extensions play some role is the Voronoi conjecture for zonotopes, and it was proved by Erdal. So zonotopes are polytopes that appear in a lot of different combinatorial problems. So those are, well, one thing that we can define them as projections of cubes. And actually, this result of Erdal is related to matroid theory, because those zonotopes that can tile the space, they actually correspond to regular oriented matroids. And the Voronoi conjecture is somehow also can be proved using that theory of regular matroids. But that's Erdal. That's not what Erdal did. He proved it in geometric way, but later it was reproved by Design, Grishukhin, and by Frank Valentin using matroid theory. So what we can do for extensions, and that's related to exactly combinatorics. So what we can do, so if we have a d-dimensional parallelohedron, and this d-dimensional parallelohedron satisfies some properties. So first, it has a free direction, I, but also its projection along this free direction is a Voronoi parallelohedron. So then the Minkowski sum P plus I has combinatorics of some Voronoi parallelohedron. And how this can be done? So actually, we can stretch it a lot, so it will be very, very long polytope like that. And there will be two parts. So one part which is in the part that corresponds to projection, and there we know that it satisfies the Voronoi conjecture, and the other part is in between these two layers, corresponding layers, and that's where actually the property that we can take that such a long segment will help us, right? So I will not go into details, so I will just say that we can prove that. So then the next part is how we can use global combinatorics to enforce the Voronoi conjecture. And actually, the approach to that was done even by Voronoi himself, right? So what he did, he let me go somewhere to picture like that. So that's what Voronoi did. So he established that it is possible. So if we have a tiling with parallelohedra, then we can check whether these parallelohedra satisfy the Voronoi conjecture or not. So we can do that basically by constructing this piecewise linear paraboloid, right? And apparently, how can we do that? So we can construct a paraboloid, and then we can try to lift those tiles that we have in our space to that paraboloid in the way that they will touch this paraboloid. And apparently, this construction relies on local combinatorics of, of the tiling, right? So, and that's if we don't have any global restrictions, then we can do that. And this can be done. So let me mention a few results. So this construction can be done for primitive d-dimensional parallelohedra, and that's the case of Voronoi. So a parallelohedron is called primitive if every vertex of the corresponding tiling belongs to the minimal number of copies of P that is possible. So D plus 1, right? So we know that if we have a vertex, then it belongs to D facets. So these are exactly D additional copies. So in total, at least D plus 1. And those are exactly the so the parallelohedra that appear as dual to Delaunay triangulations, right? So again, the classification of Delaunay triangulations that was in the core of Voronoi's reduction theory appears for primitive parallelohedra, and that's the theorem that Voronoi proved, right? So that the Voronoi conjecture is true for such parallelohedra. Actually, this definition of Voronoi parallelohedra describes local structure, right? So basically, it shows that at every vertex we have kind of dual simplex, and this can be relaxed a little bit to the case of K-primitive parallelohedra. And that's the parallelohedra where some K face, for some K, every K face belongs to D plus 1 minus K copies. And the case of Zhytomyrsky, so again, let me cross that out, something about belts, right? So the case of Zhytomyrsky, that he proved the Voronoi conjecture for D minus 2 primitive D-dimensional parallelohedra, and actually it means that all projections are hexagons. The next thing, and it also deals with local combinatorics, right? So that's the definition of dual cell. And that's basically what are the dual cells. So dual cells are expected faces of the dual tiling, right? So we know that if we have a Voronoi tiling, then there is a dual tiling, which is the Delaunay tiling. But for tiling with general parallelohedra, we do not know whether there is a dual tiling or not, but we can expect one, and we just take the combinatorics of this dual tiling, so we can read the combinatorics of this expected dual tiling from the polytopes that are incident to some face. So if we have a k-dimensional face, then if we take all the centers of the polytope incident to that k face, then we're going to get what is called a k-cell. And basically, those are the expected tiles of the Delaunay tiling, but we don't know whether they are tiles or not. And Delaunay himself, in his proof of the Voronoi conjecture for four-dimensional case, he listed all dual 3 cells, and actually those are the possible Delaunay cells for 3-dimensional lattices. So these are tetrahedra, pyramids, octahedra, hexagonal prisms, and parallelepipeds or cubes, right? And in 2005, Andrei Wardin in his PhD thesis proved that if we use only 3 dual 3 cells, then the Voronoi conjecture is true. And actually, our next approach, right? So let me skip a few slides, right? So there is additional condition that where it is, I think it's here, right? So we can construct the same piecewise linear paraboloid for many parallelohedra, and actually what we need to do, we just need to make sure that we will not have any topological restriction to do that. And how can we do that? So we can construct the pi surface of the parallelohedron by removing all non-primitive faces of codimension 2 and identifying 2 points. And then for all these pi surfaces, we can check certain topological condition. And well, let me scroll back once again. So that in that case, we can check that additional topological condition for all 5-dimensional parallelohedra, right? And as a corollary, right, so if we have a 5-dimensional parallelohedron that has a free direction, then it satisfies the Voronoi conjecture because its extension will have combinatorics of one of those Voronoi parallelohedra, and all those Voronoi parallelohedra have this combinatorial property. Okay, I think I need to stop. So let me just add what is left. What is left is careful analysis of dual 3 cells and dual 4 cells. But there are a lot of different cases. So basically, we consider all possible parity classes in 5-dimensional lattices. So there are 32 cases. Not all of them needs to be analyzed in each case, but sometimes we, I think, can go up to 20 cases in one lemma. And I think I can stop here. So thank you for your attention. I didn't have much time to talk about the proof, but at least the history and the problem, hopefully it was relatively interesting.
It's really interesting.
It was very interesting. Thanks, Alexey.
Yeah, it's very nice talk. So we had quite many questions, but maybe we have a few questions more.
Is there any hope like for the general case of the conjecture? Because it looks like still it relies on a lot of case analysis, like big case analysis, and required in particular this knowledge of possible structures and in many cases.
It's I don't think that with the same approach we can do the general case. Even for 6-dimensional case, it's really tough to answer. One thing, so remember there was 110 244, 5-dimensional. So
That
in
should
6
be huge, yeah.
right, so that's R5. So in R6, there are more than 10 to 5 times 10 to the 8th polytopes. And actually not just polytopes, but primitive ones. So the Delaunay triangulation. So here we have only 222 Delaunay triangulations, and they transform into that huge number in dimension 6. So it seems that enumeration is impossible. And actually our proof relies on enumeration because we use that combinatorics is enough, right? So, and we check that combinatorics for every polytope. So the same approach will not work, but maybe something else will be. So actually, it's kind of puzzling that, well, I said that there is this topological condition or local topological condition on combinatorics, basically, and we don't know even a single polytope that doesn't satisfy that condition. Right, so all that we know will satisfy this condition. So, okay, let me show it. I think it's here, right? So that's in our paper with Andrei Gavriluk and Sasha Magazinov. So we don't know even a single polytope that fails that condition. And there are two parts. So either we can find such a polytope and then it can lead to somehow a counterexample, or at least a combinatorial counterexample, or there is no such polytope and then it should be something different, but maybe in that case we can find a proof. Because, so my answer is, I don't think that this approach can lead to a general proof, but it may lead to a counterexample if it exists.
Okay.
How it is possible that about 200 Delaunay triangulation produce 10,000 parallelohedras? Oh, yes.
Yes, so 222, and they produce 110,000 different. So basically, what can be done, right? So, and that can be done in a 5-dimensional case. So let me try to describe that in something in simple way. So instead of working with parallelohedra, we can work with dual tidings, and those are Delaunay triangulations. So these are 222 Delaunay triangulations. And now we can make kind of coarsening of these Delaunay triangulations. So we take several simplices and combine them in one larger polytope. And well, that's not that easy to do because we still have to have a face-to-face tiling with convex polytopes, which is respected by central symmetry and translations by lattices, but it is possible to do that kind of computationally. And that's where we will get those 110,000 of different tilings, right? Because there are many ways to do that for 5-dimensional case. Particularly for 5-dimensional case, each simplex will be of volume 1/6 factorial, right? So that's 1/a lot, 1/720. So there are going to be many classes of simplices that we're dealing with. So that's why there are many ways to do that. Well, actually, some of them will be not 1/6 factorial. A few will be 2/6 factorial. So that's what is possible in 5-dimensional case. But still many options to do that.
Thank you.
Okay, thank you, Losha.